This is lesson 8.5, exponential growth functions. Exponential functions are nonlinear. Now, up to this point, all we've worked with are linear functions. We were looking at lines in all different forms. But this is going to have a completely different form for the function, and you need to recognize it when you see it. The form for an exponential function is y equals ab to the x, where a and b are both numbers, so you're going to have a variable as the exponent and a variable as the value of the function. So an example of an exponential function is y equals 3 times 2 to the x. Now, exponential functions are not lines. Remember, lines are written in the most common form, the one we usually use when we graph, function form, y equals mx plus b. The difference is here that in exponential functions, the x is an exponent. So every time you raise x, the function increases exponentially. That is a lot more than it would in a linear function, in a slope kind of form. If you look at this linear function here, y equals 3x plus 2, and you evaluate the value of the function when x is 0, 1, and 2, you're going to find that as you increase x, y increases by the same amount every time. So when x is 0, y is 2. And when x is 1, y is 5. And when x is 2, y is 8. And the pattern would continue as you increase x by 1. Every time you increase x by 1, y increases by 3. That's because 3 is the slope. So it doesn't matter how high a value x is, that slope is always consistently going to increase by 3. That is what the definition of a linear function is it doesn't change over time. Okay? But in an exponential function, that's not true at all. If we do the same thing for y equals 3 times 2 to the x and evaluate it for x equals 0, x equals 1, and x equals 2, you're going to find that when x equals 0, y is 3. And when x equals 1, y is 6. If you stop there, you might think, oh, you're just adding 3 each time. But look what happens when you calculate x equals 2. When you do that, y equals 12. Okay, so something different is happening here. You're going to see that the value is being multiplied by something every time. So to get from 3 to 6, we multiply by 2. And from 6 to 12, we multiply by 2. Which would mean when x equals 3, chances are you're multiplying by 2 again. It's going to consistently go up by a factor. And that factor is very important. Okay? This common factor in this case would be 2. So what we're going to do is look at writing a function rule from the data. We're going to look at a chart full of data, and we're going to see if we can write the equation knowing it's an exponential function. Okay, so I want you to open up your books and look at the chart, which is in example 1 on page 520. Okay, so take a second, pause this if you need to, so you can all make sure you have your books, rather than me recreate the data here. When you look at that chart, you're going to see that the y values are being doubled with every one increase in x. Okay? The fact that y is being increased by a factor every time tells you right away this is an exponential function, because that's what it is by definition. Okay? So if you look at what the multiplication factor is here, that's a very important part of the equation. That is actually the b in y equals a times b to the x. So the first thing we always do when we look at exponential data is look at what y is being multiplied by to increase. What is that increasing factor? And in this case it's 2. So right away we know that our formula starts as y equals a times 2 to the x. Now we have to figure out what a is. So to find a, you want to know what the value of the equation is when x is 0. Because remember what that means. By definition, anything raised to the 0 power is 1. So if we put 0 in here, okay, That's going to make this whole factor 1, which would mean y equals a. I hope you see that, okay? Y is a when x is 0. So if you look in that chart, they tell you when x is 0, y is 8. And if y is a, then 8 is a. Okay? Look at that and make sure you understand that. Because now that you have a and b, you can write your equation. It's y equals 8 times 2 to the x. All right, I want you to try one now. So look at the guided practice at the bottom of the same page. I want you to pause this slideshow and try to write the rule for the function. Okay, give everybody some time to do it, and then you can restart this and I'll walk you through it. Now this is the data from the guided practice. To write the function, you have to look at how y changes with x. And you can see that's what I'm doing here. I'm looking at the difference between 3 and 9. What did I have to do to 3 to get to 9? What did I have to do to 9 to get to 27? What did I do to 27 to get to 81, and so on? If it's an exponential function, 1, you're going to be multiplying by something each time, but 2, it's going to be a consistent number every single time. Okay, so when you look at this, I hope you realize that y is being multiplied by 3 every time. Okay, 3 to 9, 9 to 27, 27 to 81. That means the b value is 3. So right away you can fill that in. Y equals 8 times 3 to the x. But to figure out what the a value is, you have to look here, okay, right here, where x is 0. Because when x is 0, y is a. And you'll see that y is 27 there, so a is 27. So the equation for this exponential function is y equals 27 times 3 to the x. Now, in order for this to work for you to be able to see this and do this, you have to make sure that your data is arranged in the right way. So you want to make sure that your x's are increasing from left to right, one by one from left to right, okay? Now we're going to look at graphing exponential functions, and we're going to do this in the most simple way possible, and that is to use an input-output table. And then we're just going to plot the points. I think when making an input-output table, the simplest thing to do is to use the smallest numbers. Now you could use any numbers you want, but I like to see how the curve crosses the y-axis, so I pick points on both sides. In other words, I pick both negative and positive points, and I think working with smaller numbers is easier. So I usually use -2, -1, 0, 1, and 2. Now you're probably saying, why is she using 5? When we did lines, we were only using 3. Well, with lines, you know that the slope is consistent, so once you get those 3 points plotted, you can continue that line into infinity and it's never going to change. It's always going to go up or down by the same amount. But a curve doesn't work that way. It's going to change with every increment of x. So to get the most basic curve, you have to have at least 5 points. That's the way we're going to graph them. So I want you to be plotting 5 points every single time. Okay? So in this one, I took a really simple exponential function, and that is y equals 2 to the x. Some of you might be looking at this now and saying, but where is the a? The a would be 1 in this case, okay? So y equals 2 to the x. And what I did was I went from -2, -1, 0, 1, and 2, and I calculated what y is. This is why at the beginning of this chapter we worked on negative exponents, because you have to be able to calculate 2 to the -2. Remember, that's 1 over 2 squared, and that's how I got that 1/4. So hopefully you're not confused about that. I took my y values and I plotted them on this graph. So if you'll take a look at this, you'll see in the blue points, when x is -2, I have y at 1/4. No, it's estimated as best I could on the size graph paper. And then at 1/2, and then at 1. And you'll see how the curve starts to increase. And if we went further, you're going to see that the curve actually starts to go up much sharper. On the left-hand side, if you went and plugged in -4, -6, -8, you would see that the line hugs the x-axis, but it never crosses into negative values. You might want to try that just so that you know what I'm telling you is the truth. But believe me, it is. Um, when you look at this, you have to be able to recognize what the domain and the range are. Now for the domain, those are the x values, remember? It could be any real number. You could put in -10, you could put in -800, you could put in +10, you could put in +250. It wouldn't matter. You could do this with this curve. So the domain's all real numbers. But the range is only all positive real numbers because this curve is never going to go into the negative range. So what you want to do is plot these points and draw a smooth curve through them. Now, it's not easy for me to do this with a mouse, so I'm not going to connect them for you because it's just going to look like a mess. But you want to do that when you graph these, if you would please. Now we're going to compare some graphs of exponential functions, and you'll see my great graphing expertise here with a mouse. But I want to show you what happens to different curves depending on what you do to the function. So I did 3 functions here. The first one is the one that I just graphed on the previous slide, and that's y equals 2 to the x, and that's the graph in the blue. Okay, so you can see that it hugs the x-axis all the way down on the left, but then once it crosses the y-axis, it starts to curve almost straight up. When I multiply that function by 3, what that does is it increases the slope of the curve. It's going to make it sharper. So when I start to plug my numbers in and do my input-output table, you're going to see it's going to rise much faster. Now down on the left-hand side, it's going to be almost on top of or very close to what we had before. But as you start to increase the x values, it's really going to take off. The same way, if I change the coefficient to a negative number, like -3 instead of +3, that's going to be an exact mirror image of the green graph. Now, I know my graph doesn't look like an exact mirror image, but it would be if you could draw it perfectly. Now, we're going to talk about exponential growth. Okay, now exponential growth only takes effect, only works when a is greater than 0 and b is greater than 1. Okay, that's exponential growth. So we take our basic model we looked at before, ab to the x, and we're not looking at a fractional exponent here for growth. Okay, it's going to, in other words, things are going to get bigger as we go forward. And what we're looking at is something's increasing by the same percentage every time period. And usually when we think of this, we think of interest, or we think of an increase in value of something, like a painting, but it also could be an increase in population, especially in nature. Population of animals usually don't increase linearly. They usually increase exponentially, especially animals like rabbits, for example. Okay, so here's the exponential growth model, and it's y equals a times the quantity 1 plus r raised to the t. Now, in this model, a is the initial amount, r is the rate, and t is the time. You have to make sure your rate and time are in unit agreement. So in other words, if your rate is per year, your time must be in years. We call 1 plus r, that group in parentheses, that's called a growth factor. So for example, if you're getting 2% interest per year, 1.02 would be your growth factor. So here's the example. The owner bought a comic book for $55 in 1980, and the value of the comic book increased at a rate of 2.8% per year. So we're going to write a function that models this. So what you do is you put the initial amount in, 55, and you multiply it by 1.028 and raise it to the t. Whenever you write the function, don't be specific about t, just put it as t. So to calculate the value in 2005, you use t as 25. So you're going to raise that to the 25th power, and you're going to get $110. This is the formula we use for compound interest as well. So take a look at that example in your book.